Hi, welcome to the Berean Builders Discovering Design with Physics, Chapter 10, Review Questions. Let's go ahead and get started. So we're going to skip these definitions since those are so easily found in the book and start with number 2. A system is displaced from equilibrium and it exerts a restoring force. If the displacement is up, what is the direction of the restoring force? And so simply that answer is going to be that the restoring force is directed down. And that's because restoring force, by definition, is opposite of the displacement. For question 3, the graph on the right shows you the results of an experiment similar to experiment 10.1 that you should have done at this point. Do the results of the experiment demonstrate Hooke's law? Why or why not? And so the results of this experiment do not demonstrate Hooke's law because the data don't form a straight line. If we are conforming with Hooke's law, then these data points, when we connect them, would form a straight line. And this is clearly curved. Hooke's law says that the force is directly proportional to the distance from equilibrium. And so that's going to form a straight line on this kind of graph. For question 4, spring A has a force constant of 13.5 newtons per meter. Spring B has a force constant of 1.56 newtons per meter. Spring C has a force constant of 245 newtons per meter. Which spring is hardest to stretch? And that's of course going to be spring C with the highest force constant. And that's because the larger the force constant, the more that spring is going to fight being stretched from that equilibrium position. For question 5, a spring is hung vertically and then a 175 gram mass is hung from it. If the spring constant is 12.4 newtons per meter, how far from its unstretched length will it stretch? So let's write down what we are given. We have a mass equals 175 grams, and I'm immediately going to convert that to kilograms. And we're given the spring constant, our K, equals 12.4 newtons per meter. And that K always has that newtons per meter unit associated with it. And we want to know how far from its unstretched length it's going to stretch when that mass is hung from it. So what we're wanting to know is the delta x. Okay. So the equation that we have that has delta x in it is equation 10.3. And that is that force equals our negative spring constant times the delta x. Okay, we are given the spring constant, but we don't have the force directly at this point. But because we're given mass, we can calculate the force. The force in these equations is generally just the weight, okay? So force is in newtons, weight is in newtons, and so we just need to calculate the weight given this mass. So let's do that. Weight, which is a unit of force, right? So we could say force equals weight equals, and we're going to do the mass times the acceleration because that's what force is. But when we're talking about weight, of course, that acceleration is gravity. So we have our mass, 1.7 or 0.175 kilograms, times our acceleration, which we're going to use gravity, so 9.81 meters per second squared. And when we do that, we're going to get our force equals 1.72 newtons. And we'll go ahead and check our units. Kilograms times meters per second squared is a newton. And so we're going to write newtons there. So now that we have the force, we have two of the three variables that we need to solve for the third variable. And let's go ahead and rearrange this, right? And so we're solving for delta x, and so that is going to be the force divided by the negative constant. And so let's go ahead and plug everything in here. We have the force of 1.72 newtons, and our constant is 12.4 newtons over meters. And we make sure we remember to put that negative sign in there. 12.4 newtons over meters. And when we divide that, the newtons are going to cancel. That meters is going to go up into the top, and we will get negative 0.139 meters. Now this negative makes a lot of sense because when we are hanging something down from the bottom of a spring, the displacement is going to be down or negative. And so we have this exactly right. However, when we write out the answer, we don't need to have that negative. The spring will stretch 0.139 meters. Okay, and the reason that we don't need to have the negative or say down, this question is just asking how far. It's not actually asking for a displacement per se, and so we can just give the magnitude of what it's going to stretch, and that is 0.139 meters. For question 6, you have two scales that measure weight. The first one says it works best for objects that weigh less than 500 pounds. The second says it works best for objects that weigh less than 50 pounds. Which one uses a spring with a larger spring constant? So the answer for this is that it's clearly going to be the first one, that is for objects that weigh 500 pounds. And that's because the larger the force constant, the more force the spring can exert or when stretched or compressed. If a scale uses a weak spring, so it's going to have a small force constant, it can only measure the weight of light objects. But if it uses a strong spring, then it can measure the weight of heavier objects. Okay, and so that's clearly what's going on here. This one has to have a smaller spring and therefore a smaller force constant because all of the objects need to weigh less than 50 pounds. Whereas this one is capable of handling objects that are up to 500 pounds, and so it's definitely going to be using a bigger spring, which has a larger force constant. For question 7, I'm going to be a little bit tricky on this one for you, and because this is something that you really should have memorized at this point, or will definitely need to have memorized for the exam for this chapter, I'm just going to refer you to page 264 in your book. For question 8, a spring is hung vertically and then a 1.49 kilogram mass is hung from it. The spring stretches 4.51 centimeters as a result. Then someone pulls the mass down an additional 15.0 centimeters and releases it. So before I start answering any questions, I'm going to go ahead and write some of the important information from this problem. We have mass equals 1.49 kilograms. We have that the spring stretches 4.51 centimeters as a result. And so that delta x at equilibrium is going to be a negative 4.51 centimeters. Okay. And of course, we don't do anything in centimeters, so I'm going to go ahead and convert that to meters. Negative 0.0451 meters. And then we're given that someone pulls the mass down and stretches it an additional 15.0 centimeters. And so that's going to be our amplitude. And let's go ahead and convert that also. There, 0.150 meters. So our first question is, what will be the amplitude of the motion? Well, because we stopped and organized all of this, we already know what the amplitude is because we just wrote it down, and that's going to be 15.0 centimeters. And we can leave it in centimeters here or use the converted 0.150 meters. Either answer is correct. We'll just leave it as centimeters for now. What will be the period of the motion? So for this, of course, we need to use our equation 10.5. And that is that period equals 2 times pi times the square root of the mass divided by that spring constant. And of course, we were not given the spring constant, and so we're going to need to calculate that. And so let's just look at this. Whenever we have an equation that we're solving for, we need to have everything but one variable given to us, right? And so here we're missing the period, which is of course expected because that's what we're being asked for, but we also need that spring constant. So let's think back and figure out what equation we could use to give us the spring constant. Well, we have equation 10.3, which is that the force equals a negative spring constant times delta x. But we're actually still missing two things here, right? We don't have the force or the spring constant in this equation. But we do know how we can solve the force. Just like this equation up here, we can determine the weight, which is the force, based on the mass that we are given. So right, and so that's mass times gravity. And so we're going to plug that in, 1.49 kilograms times 9.81 meters per second squared. And for our force, we're going to get 14.6, and that's going to be in newtons, right? Because kilograms times meters per second squared is newtons. So now that we have that, we can plug that into here. I'm first going to move things around just like I did before, except this time I'm solving for the force constant or the spring constant rather than the displacement. And so I'm going to get that my spring constant equals the force divided by negative delta x. I just took this negative and put it with the delta x. And plug everything in here. 14.6 newtons divided by, we have a negative, taking that from there, and then my delta x was a negative because it's being pulled down. I said negative and didn't write it down. 0.0451 meters. And so with that, I'm going to get 324 Newton meters. And that is my spring constant. So now I can finally take this and plug it in up here to get my period. So we have 2 times pi times the square root of our mass, 1.49 kilograms, divided by our spring constant, which is 324. Now here, this is what I was really referring to. I'm going to take this newtons and I'm going to write it out as all of its component units because that's going to help me with canceling. So for a newton, I have kilograms times meters per second squared. And then all of that is divided by meters because this is from the force constant. Okay, so canceling out, I'm going to cancel out the meters. The kilograms are going to cancel out, and I'm going to be left with second squared, which is in the denominator of the denominator. We're just going to put it in the numerator once I do that division. And which is exactly what I need because I'm looking for period, which is going to be in seconds, and I'm taking the square root of this. So it was always a good idea to just do this before you even almost start the math. Make sure you're going to come up with the right units and that you are putting in the correct equation or the correct values for the equation. So once I calculate all of this out, I'm going to get 0.426 seconds. Okay, the three significant figures. This one does not count towards what I'm doing for significant figures because it's just a 2 that's part of the equation. It's a constant number. Only these two values count for the three significant figures. So our final answer here is that the period is 0.426 seconds. For question 8C, taking friction into account, what will happen to the amplitude of the motion as time goes on? So we don't even need to use any of the information from this problem to answer this because this is just more of a defining question. Okay, and so what is going to happen is that the amplitude's going to decrease, and this is going to happen with any type of periodic motion like this because of friction. For the friction in this spring is going to convert the energy into heat, and that's going to reduce the total energy and then in turn that's going to reduce the amplitude. For D, taking friction into account, what will happen to the period of the motion as time goes on? And the period, however, is not going to change because the period doesn't depend on the amplitude. The other way to see that is to notice that the equation for period has only m and k in it. So just looking at my notes for equation 10.5, we have the period equals 2 times pi times the mass times the spring constant. And so amplitude has no factor in this, and the spring constant's always going to be the same. That's why it's called constant. The mass is always going to be the same. And so the period is not going to change due to friction. For E, suppose you did the same experiment with a larger mass. Would the period be shorter, longer, or the same? Well, let's pull this back out. Okay, and so if mass, which is in the numerator of this fraction here, was increased, then that is definitely going to make the period increase as well. And then finally F, suppose we did the same experiment with a spring whose force constant was 100 newtons per meter. Would the period be shorter, longer, or the same? Well, we calculated from this problem that the spring constant was 324 newtons per meter. And so that's just important to consider as we answer this question. And so this question is positing that the force constant is smaller than what we initially had. So let's look at where we have the spring constant in our period equation, and that is in the denominator. Well, if we have a smaller denominator, then the overall number is going to be larger. And so in this case, the period would be longer. All right, so we don't actually need to make the calculation. You could have done it if you wanted to, but all we needed to really recognize is that the spring constant is in the denominator and it's a smaller number, so that's going to lead to a larger t value. For question 9, you are observing a mass spring system in periodic motion. Using amplitude and equilibrium position, so we're wanting to see these keywords in every answer, answer the following question. So for A, at what position will the mass be traveling the fastest? And so this is going to be at the equilibrium position because the mass has been speeding up from the amplitude. At the amplitude, it stops and then it goes back up, right? And the fastest point in this whole spring system is going to be at the equilibrium position in the middle, okay? So, and then after that, it's going to slow down again. For B, at what position will the mass be traveling the slowest? Well, we just answered that, right? As it gets to the amplitude point, it's going to stop and then change direction and accelerate in that direction. And so the amplitude is the position where the mass is traveling the slowest. For C, at what position is the net force on the mass 0? And that is the equilibrium position. Equilibrium, there is no force when that delta x equals 0. And for D, at what position is the net force on the mass largest? And that is going to be at the amplitude position, because at this point, this delta x is at its largest value. And so that means the force, the F, will also be at its largest value. For question 10, a mass spring system with a 150 gram mass has a period of 1.5 seconds. What is the force constant of the spring? So we are given mass equals 150 grams equals 0.150 kilograms. And I've just made a mistake here. 1.5, right? Because in 150, this 0 is not significant. So let's fix this. Okay. And then the period equals 1.5 seconds. So t equals 1.5 seconds. And we need to know what the force constant is. Okay, so our equation that has a period, a mass, and a force constant is our equation 10.5, which is t equals 2 times pi times the square root of mass divided by the spring constant. And we're going to be solving for K, for our spring constant. We're given T and M. So let's go ahead and reorganize this. So I'm going to square both sides. And so we end up with T squared equals 4 pi squared times M over K. And so now I'm going to swap this K and the T, and so I'll have K equals 4 pi squared times M, and all of this divided by T squared. So plugging everything in, we still have 4 pi squared times our mass, 0.15 kilograms, divided by 1.5 seconds, which is going to be squared. And when I calculate all of this out, I'm going to get 2.6. and I have kilograms per second squared. And this is definitely not my spring constant, right? This should be in newtons per meters. And so I just wanted to point out to you that if we decided to multiply this times meters, which is multiplying it times 1, right? This is newtons, and that is our meters, okay? So this is 2.6 newtons over meters, okay? So if you get kilograms per second squared, don't panic, because we can multiply it times meters over meters and we end up with newtons over meters, okay? And so that's our final answer. The force constant is 2.6 newtons over meters. For question 11, what characteristic of the restoring force is necessary for simple harmonic motion to occur? So the answer for this is that the restoring force must be directly proportional to the displacement from equilibrium. Okay, we could also say that it must obey Hooke's law, because that is what Hooke's law is. You don't have to say it is opposite of the displacement, although it is, because that is the definition of restoring force, but you don't have to say that. The key thing is that it is directly proportional to the displacement from equilibrium, or that it obeys Hooke's law. For question 12, when is the potential energy of a mass spring system the greatest? When is the kinetic energy the greatest? And so saying this is equilibrium, as we go down, the potential energy is going to be the greatest at the amplitude, or top or bottom, right? The distance, the greatest distance from equilibrium. And that's because at this point, the mass stops. And so there is no kinetic energy. There's no velocity. And so all of the energy is in the potential energy at that point. The kinetic energy is going to be greatest at equilibrium. And that, of course, is because delta x equals 0. And so the potential energy at that point is 0. And the velocity is at its highest. And so that energy is completely kinetic. There is no delta x that gives any of the energy to the potential energy. And so it's all kinetic. So at the amplitude, it is all potential energy. At the point of equilibrium, it is all kinetic energy. And those are the greatest points for each of those. For question 13, a spring with a force constant of 87.2 newtons per meter is compressed 10.5 centimeters from its equilibrium position. So let's go ahead and write out what we're given. We have our K, our spring force constant, and that is 87.2 newtons per meter. And we are also given this compression, 10.5 centimeters from its equilibrium position. So this is the key word, because when we are given this value, we're almost never going to be told it is the amplitude, okay? But it is a displacement from its equilibrium. And so this 10.5 centimeters equals our amplitude. And of course, we're going to convert that to meters. Right there. So our amplitude is 0.105 meters. So now for the actual question part of this, what is the total energy in the system? So as we just discussed, when we are at the amplitude point of the spring system, then all of the energy is in the potential energy there. But we have this equation equals 1/2 of the force constant times our amplitude squared. And so now we can just plug everything in. So equals 1/2 of 87.2. I'm going to go ahead and write out the newtons. So we have kilograms times meters per second squared, and this is our force constant, so we're dividing it by meters. Okay, so these meters we know are just going to cancel. Times our amplitude, 0.105 meters squared. So we're going to end up as kilograms times meters squared per second squared. And of course, that is a joules unit. And so that's exactly what we want to see. So we end up with 0.481 joules. Okay. For B, if a 2.5 kilogram mass is attached, how fast will it be moving at the equilibrium position? So we're going to add just one more variable that we know. Our mass equals 2.5 kilograms. And at equilibrium, we know that all of our energy is kinetic, right? That's what we discussed here in question 12. So if all of our energy is kinetic, so now we know that for this question, our kinetic energy equals 0.481 joules. And we can use way back when, 2 chapters ago, equation 8.3, where we had kinetic energy equals 1/2 of the mass times of the velocity squared. We're going to be solving for velocity, and that is going to, when we solve for velocity, we're going to have velocity equals, it's going to be the square root of 2 times the kinetic energy divided by our mass. So plugging everything in there, we have 2 times 0.481. I'm going to write out what joules is. So we have kilograms times meters squared over second squared. And we're dividing, of course, by kilograms. So kilograms cancel, and we're going to have meters squared divided by second squared. And when we take the square root, it's meters per second, which of course is velocity. And of course, we have 2 significant figures because the mass is in 2 significant figures. Our final answer is that it will be moving at 0.62 meters per second. Now, just make sure you don't make the mistake that saying the velocity is 0.62 meters per second. The question is asking how fast it will be moving. So we don't need a velocity. We don't need to add a direction to this. And in fact, we don't know what the velocity is when it comes to direction because it didn't tell us which direction it was moving at equilibrium. Okay, is it moving up or down? We don't know, but anytime it reaches equilibrium, it is moving at this speed. at 0.62 meters per second. So you can say it will be moving at 0.62 meters per second, or the speed is 0.62 meters per second, but don't use the term velocity. For C, how fast will that mass be moving when it is 5.0 centimeters from the equilibrium position? So now we have another variable that our delta x equals 5.0 centimeters. We'll convert that to meters. So 0.050 meters. Okay, so knowing that our total energy is the sum of our kinetic energy and potential energy, we need to determine what each of these are at 5.0 centimeters, or at least use the equations for these so that we can determine what the velocity is at this point. So our total energy is what we determined before, right? Let's just write out everything. Okay, so instead of writing total energy, actually, we'll go ahead and write it out. So total energy equals kinetic energy plus potential energy, right? And let's write these out in terms of the equations that work for these the spring mass systems. So our kinetic energy is 1/2 our mass times our velocity squared, and our potential energy is 1/2 our spring constant times our delta x squared. Okay, so let's look at what all we're given. We know the total energy from before. It's 0.481 joules. We have the mass. We need the velocity. Do we have our spring force constant? Yes, we do. Okay, we have that, and we have our delta x that was just given to us. And so we just need to solve for velocity here. So solving for velocity, I'm going to get doing all the kind of behind the scenes work here, but it's going to be 2 times this total energy minus 1/2 of the spring constant times the delta x squared. Okay, so 2 times the total energy minus the potential energy, and dividing that by the mass. If you work this out and you just fill in the numbers and then solve for V, that's great. Do that. That's fine. You'll still get the same answer as me, or very, very close to it. So now I can plug everything in. So I'm going to have 2 times our total energy from before, 0.481. And just like before, I'm going to, instead of saying joules, I'm going to write it all out. So kilograms times meters squared per second squared. And then subtracting, here I have the 2 times the 1/2, that's going to cancel, okay? And so I'm just going to subtract, it's going to be 1, right? So I'm going to subtract my constant, 87.2. Again, I'm going to write it out instead of putting the newtons. So I'm going to put kilograms times meters per second squared times meters, which is newtons per meters, times 0.050 meters, and this is squared. This is my delta x. And then dividing all of that by my mass, 2.5 kilograms. And so putting all of that in my calculator, I'm going to go ahead and do this math. I always like to do this addition subtraction math first because we might end up with an issue with significant figures that changes our overall answer. And so when I do the first part of this, I'm going to get 0.962 meters squared per second squared, right? And just showing you up here, the kilograms canceled and the meters canceled here. And so you have meters squared per second squared for both of these units. Minus 0.218 meters squared per second squared, because I was able to go to 3 significant figures for both of these. So it actually either way would have worked, whether I had done this all in one straight shot or done the addition and subtraction separately, like I just did, because it goes to the thousandths place in either case. But it's always a good idea to do that just in case. Oh, and the kilograms already canceled, so I'm not going to write that here. Okay. And so then we're taking the square root. And we're going to get 0.55 meters per second. Now, you may have gotten something a little bit different if you had done... if you had plugged in all of the numbers and then solved for velocity, you might have gotten 0.54. Always remember, if you're within plus or minus a couple hundredths plus or minus a couple of the significant digit, the last significant digit, then you're good. So it will be moving at 0.55 meters per second. Again, can't use the term velocity. We don't know which direction it's moving, and it doesn't matter for this question. Question 14, a 512 gram mass is hung from a vertical spring, and the mass causes the spring to stretch 4.5 centimeters. The mass is then pulled down farther and released. When the mass reaches the equilibrium position, it is moving with a speed of 2.1 meters per second. How far was the mass pulled down? So let's write out what we have. We have mass is 512 grams equals 5.12 kilograms. Then the mass itself causes the spring to stretch 4.5 centimeters. This is different from pulling it, okay? This is what the mass is doing. And so this means that at equilibrium, delta x equals 4.5 centimeters. This is a little bit of, I will admit, a confusing part of this chapter, because sometimes the delta x is our distance from equilibrium, and sometimes it tells us what the stretch is at equilibrium itself. And I should have put, it's a negative 4.5 centimeters. That spring is stretching down. Okay, but key thing here is it tells us then the mass is then pulled down farther. Okay, and so we have a further delta x, and in this case, it's a special delta x that's pulled down the farthest it's going to be pulled. And so that is going to be the amplitude, okay? And that, of course, is what we're being asked for at the end of this question. So amplitude is a big question mark. When the mass reaches the equilibrium position, it's moving with a speed of 2.1 meters per second. So velocity at equilibrium equals 2.1 meters per second. So this question is kind of pulling together everything about the spring mass systems in one big question. So to understand how far the mass was when it was pulled down, of course, we're going to need our total energy equation, right? So total energy equals 1/2 of our spring force constant times our amplitude. But there's two things we don't know here. well, there's a lot we don't know here. We don't know the total energy, we don't know the spring force constant, and we don't know the amplitude. So we're going to need to understand a lot to get to this point. But we know that we were given enough information to give us the delta K, right? So if you remember our equation 10.3, force equals negative K times delta X. Now, we don't have the force. We do have the delta X because this delta X is referring to equilibrium, okay? Our force constant is based off of the equilibrium delta X. And we can get the force based off of the mass. So let's do that first, right? Force equals mass times gravity equals 0.512 kilograms times 9.81 meters per second squared. And then for our force, we're going to get 5.02 newtons. And so now we can solve for K. K equals our force divided by a negative delta X, which equals 5.02 newtons divided by a negative delta X is negative 4.5 centimeters, which I didn't do a good job here because I should have converted it into meters. So negative 0.045 meters. So negative. And we get 110 newtons over meters is our K. So now we have one part of this. And we need the other part of this, which is our total energy. So how can we determine that? Well, we have this velocity at equilibrium. And so with that, we can determine the kinetic energy. So our kinetic energy equals 1/2 mass times velocity squared. And we know at equilibrium, kinetic energy equals total energy. So we could even just say, this is total energy. And so let's plug everything in here. We have 1/2 of the mass, 0.512 kilograms, times our velocity, 2.1 meters per second, squared. And we would get 1.1 and kilograms times meter squared per second squared is going to be joules. So now we have total energy that we can plug in here. We have our spring force constant that we can plug in here, and we can solve for the amplitude. So let's solve for amplitude. And with that, we're going to get amplitude equals the square root of 2 times the total energy divided by our spring force constant. So we have 2 times 1.1, and I'm going to go back to writing it out, kilograms times meters squared per second squared, divided by the spring force constant, 110 newtons. So we have kilograms times meters per second squared times meters. So let's go ahead and make sure that we are going to end up with the right units. These meters will cancel. These second squareds will cancel. This kilograms will cancel. And we're going to be left with meters squared in the numerator, which when we take the square root is going to be meters. So we are good on the units. And when we calculate all of this out to two significant figures, we're going to get 0.14 meters. So the mass was pulled down, because that's what it's asking. How far was the mass pulled down? .14 meters. For question 15, two simple pendulums are made. The first has a length of 15.0 centimeters and uses a bob whose mass is 12.0 grams. The second has a length of 11.5 centimeters and uses a mass of 25.0 grams. Which has the shorter period? And the answer here is that it's going to be the second pendulum, because it has the shorter length, 11.5 centimeters versus 15.0 centimeters. The length is what is important with the period of a pendulum. And the mass is actually completely irrelevant. This was just a little extra information that we didn't need. For question 16, a simple pendulum is displaced 11.0 degrees from its equilibrium position and then released. After being observed, it is stopped. It is then displaced 35.0 degrees from its equilibrium position and then released. In which case will it exhibit simple harmonic motion, and why? So it's only going to exhibit simple harmonic motion in the first case, and that's because a pendulum can only do simple harmonic motion if the angle is small. So in the first case, we have 11.0 degrees. In the second case, 35.0 degrees. And this is the only one that is small. It needs to be less than 20 degrees. It has to be small because that is when the restoring force is directly proportional to the displacement. Question 17, Mr. Spock is on a planet whose acceleration due to gravity is 15.6 meters per second squared. He whips out his handy 15.0 centimeter simple pendulum and puts it in simple harmonic motion. What is its period? So we are going to use equation 10.11 here. It's T equals 2 pi times length divided by gravity. So our gravity in this case is 15.6 meters per second squared, and our length equals 15.0 centimeters, which is 0.150 meters. And all we need to do is plug it in. So T equals 2 times pi divided by 0.150 meters divided by our gravity, 15.6 meters per second squared. Right, so this is going to give us meters that canceled, second that goes in the numerator, and the second squared, square root of that, we have the right units. And that calculates out to 0.616 seconds. The period is 0.616 seconds. Pretty simple. Question 18. A grandfather clock is made so that each time the bob reaches the amplitude of the motion, 1.0 seconds have passed. In other words, a tick indicates 1.0 seconds have passed, and the following tock indicates another 1.0 seconds have passed. What is the length of the pendulum on a clock? So if you're not visualizing this well, Let me actually try to draw a straight line here. Okay, so we have the pendulum and the amplitude. There's an amplitude on either side. Okay, and so this tick is 1.0 seconds, and this tock is 1.0 seconds. Okay, and so the full period is going to be 2.0 seconds, right? The full time it takes from go to one side to the other is 2.0 seconds. Then what we need to determine is the length. And so we're going to use that same equation, T equals 2 times pi times the square root of the length divided by gravity. In this case, we're assuming it's Earth, so we have the gravity, and we just need to determine the length. Length is the only thing that we don't have for this equation. So let's solving for length. We're going to get T divided by 2 pi, and all of this squared times gravity. And we can plug that in. So we have 2.0 seconds divided by 2 pi squared times 9.81 meters per second squared. And with that, we get 0.99 meters. The length is 0.99 meters. Final question here. What is the purpose of winding a clock that uses a pendulum to keep time? Well, we know that friction is going to cause that pendulum to slowly decrease in amplitude until finally at some point it will stop just due to friction. And so winding a clock stores the energy that can then be given to the pendulum to replace the energy that friction converted to heat, so that it can still keep ticking with the same amplitude and keeping time. So that is it for these Chapter 10 review questions. As always, if you have any questions, leave them in the comments. Thanks.